All right, so this is part 5 of the continuing education lectures. We're going to switch to probability now, and I'm going to start with one of many examples of how you can manipulate people by how you present information. And over lunch, we were talking about how this is done all the time. So I tell you, you've won 3 of the last 4. So that's a 75% or 750 winning percentage. Is your team doing well? If you're a Patriots fan, actually 750 winning percentage is actually a bad season. But for most of the world, 750 is a pretty good winning percentage. What other information is almost surely true if I've told you you've won 3 out of the last 4 games? You lost the game before that. So if you look at the games, 1, 2, 3, 4, 5, we must have a loss 5 games ago. If we didn't have a loss 5 games ago, I would have said we've won 4 out of 5 because that would sound better. Okay, what else do you know?
You won the 4th game.
You won the 4th game, because if we had the loss here, I would have said we've won 3 in a row. So now, I know we're 3 of 5, which is 60%. Or if you look at the last 3, it has to be 2 wins and 1 loss. Or 2 of 3 for roughly 66%. So this is just one of many examples of how easy it is to manipulate expectations. How you phrase things is extremely important. Okay. So what I want to do now is I want to do Stirling's formula. This is one of the most beautiful results in mathematics. And I want to give an application of this to proving one of the most important formulas in mathematics, the central limit theorem. So the further you go in mathematics, you eventually reach classes where you start using the word fundamental theorem. And I tell my students, whenever you hear something like fundamental, this means important. So in high school, there are 2 fundamental theorems you might have met. The first is you might have met the fundamental theorem of arithmetic. Any integer can be written uniquely as a product of primes. So I can write any number n as p1 to the r1 times pk to the rk, where I'll assume p1 is less than p2 is less than pk. And if I put the primes in increasing order, the fundamental theorem of arithmetic says I have a unique decomposition. So for instance, if I give you 48, so this is 6 times 8, or 16 times 3, so this would be 2 to the 4th times 3. And the only other ways I could write 48 is I could do something, I could do 2 times 3 times 2 cubed. I could play games like that. So let me just put them in increasing order like this so I have some kind of unique way of writing. So how many of you have done fundamental theorem of arithmetic at some point? Okay. All right, you might have done the fundamental theorem of algebra. So polynomial of degree n has n roots. And you could have multiple roots. If I give you x squared equals 4, then the roots are going to be plus or minus 2. So okay, so I have distinct roots here, so that doesn't work. So I could do x squared minus 4 squared equals 0. So now the roots will be plus or minus 2, plus or minus 2. So really, if I want to write them all explicitly, it would be minus 2, positive 2, positive 2. So how many of you have done the fundamental theorem of algebra? Okay, a little bit more. Then the next is the fundamental theorem of calculus. And the fundamental theorem of calculus says if I give you some curve like this, and this is my function f, then the area under the curve from a to b is the antiderivative at b minus the antiderivative at a, where big F prime is little f. And this is why we care so much about calculus and integration, is it gives us areas under curves, and a lot of times these areas under curves are probabilities. So these are the first of the fundamental theorems you often meet as you start going through your education. In probability, we don't talk about the fundamental theorem of probability. We call it the central limit theorem. So centrals, at least if you listen to it, seems close enough to fundamental that it should be natural that this is one of the things we should care about. So if you're teaching statistics, a lot of our statistical tests are based on the central limit theorem. And the goal is to give you a little bit of a sense of why is the central limit theorem true. And so I'll briefly state what the central limit theorem is. So central limit theorem, in a shock, abbreviated CLT. And it basically says the following. Imagine you have a bunch of random variables, x1, x2, ... xn. So we often use capital letters to denote a random variable in math, and we use lowercase to take on the value. So capital X might be the number of Super Bowl wins the Patriots have, and as of today, the value of that would be 5. Okay? We will often assume that they have identical distributions. It's not needed, but it makes things a little bit easier. We'll assume they have a finite mean mu, a finite standard deviation sigma, and I'll just say good decay. So the probability of a large event isn't too large. And the further out you go, the less likely it is. So most of your random variables will have this nice decay. The technical condition is if your distribution is continuous, you want this integral to be less than infinity for each k. So this is your probability distribution, and this is calculating what's called the Kth moment. This is a stronger condition than we need. We really only need that this is true when k equals 3. But there's just some decay. Then the following is true. The sum of our random variables. Well, if each one of them has mean mu, that's the expected value. So most students understand intuitively what the concept of a mean is. They're always very concerned, how do they do relative to everyone else in the class? So I would expect each one of these to be fluctuating about the mean. Since I have n of them, I expect the size of this should be what? So about n mu. So I'll subtract off n times the mean. And then the standard deviation tells me the right scale to study things. And this is a little bit more involved. It turns out as you add more and more copies, it's going to spread out more and more. That makes sense, because things can fluctuate, so you have more of a chance of being far out because you're adding more and more times. Think of it as rolling die. If you roll just one die, what's your average value? 3.5. If you roll 2 die, your average value is a 7. And you can start looking at how the values are spread out. And if you roll 1 die, the values are spread from what? From 1 to 6. If you roll 2 die, they're spread out from 2 to 12. They're spread out over a longer range. And in fact, if you look at the probability distribution of 2 die, it's basically a triangle. There are 6 ways of getting a 7. There are 5 ways of getting a 6 or an 8, all the way down to 1 way of getting a 1 or a 2. And so it turns out that the correct scale to study this is you divide by the standard deviation times the square root of n. And so when you add more and more copies, this is just telling you how things should grow. And it turns out that this converges to a normal distribution with mean 0 and standard deviation 1. So I'll explain exactly what a normal is later, but I don't have to subtract off this. I don't have to divide by this. They're just constants. They depend on n, but they're just constants for a given value of n. This is to standardize things so I can compare apples and apples. How many of you still make your students learn log tables? Okay, good, right? There's no need in the 21st century to learn log tables. In the old days, Does everybody know what a log table is? And you can have log tables for different bases. But you really only need log tables for one base. And the reason is, if you want to calculate the log of x base b, this is the same as the log of x base c over the log of b base c. This is called the change of basis formula. And what this tells you is, if I want to calculate logs in base b, if I know how to do logs in base c, I can pass from that knowledge to logs in base b. I only need to construct one such table. Now, you will often find tables with more than one base. Why would you find tables with more than one base? Convenience. Nothing other than convenience. What are the bases you might want? You might want base 2. You might want base e, the natural log. You might want base 10. So, let's just have 3 pages. But you really don't need the 3 pages. You can do it with 1 page. Over here, similarly, I don't need to have this normalization. But by doing this, I've now converted it so that they all are going to the same distribution. And the normal with mean 0 and standard deviation 1 is the following. So normal with mean mu and standard deviation sigma. Is everybody familiar with the concepts of the mean and the standard deviation? Standard deviation is just how much it's spread out. Mean is the average value. So most students want to know what the mean was. The more grade conscious ones might want to know the standard deviation, how spread out it is. Years ago when I was an undergraduate at Yale, and I know this is being recorded, I was visiting a friend of mine at Harvard, and I noticed that the professor for one of the pre-med classes gave the first 4 moments of the distribution. They also gave the skewness and the kurtosis. So you could really see how you were doing relative to your fellow classmates. So the density is 1 over the square root of 2 pi sigma squared e to the negative x minus mu squared divided by 2 sigma squared. So this is the normal with mean mu and standard deviation sigma. So the standard normal is just mu equals 0, sigma equals 1. And that would just be 1 over the square root of 2 pi e to the negative x squared over 2. And what it's saying is this is going to converge to that. So if I want to calculate the probability of certain events, instead of calculating what the actual value is, I could actually just approximate it with this. So if I'm rolling 2 die, the 2 die is a triangle. That's not a terrible approximation, but it's not great. Typically, once you have on the order of 30 observations, the normal is a really good approximation. If you want a painful calculation, calculate the probability distribution for adding 3 die or 4 die. You can do it. So if you roll 4 die, it goes from smallest value of 4, largest value of 24. And what's the likely value if you do 4 die? 14. As you look at all the different ways. And in fact, the easiest way to do with 4 die is to do 2 sets of 2 die. And so if I want to get a number like 9, my first 2 dice could give me an 8, or no, could give me a 7, and the second dice could give me a 2. And look at all those possible. It gets painful very quickly. You can write down the closed form expression, but it's painful. If you have a large number of die, it's much nicer to use this approximation. And this is the basis of a lot of statistics. So what I want to do is I want to show you Stirling's formula for the factorials of large numbers, show you a little bit about binomials. These are coin tosses, yes, no, on, off, and show you how that this leads to this as an approximation. The first thing I should probably do is prove to you that this is a probability distribution. So I have to show that this integrates to 1, that the area under the curve is 1, and that it's non-negative. Non-negative is not so bad. The fact that it integrates to 1 is a lot harder. So the best way to show that it integrates to 1 is I need to do a polar trick, and I need to integrate in polar coordinates. How many people have seen polar integration? Well, let me see the hands up. At some point in your life, have you seen polar integration? All right, so what I'm going to do is I'm going to just do this fast at warp speed, okay? Just to show...
A little less than warp speed, please.
A little bit less than warp speed. Okay, but I don't want to get into too much detail as to why certain lines are true, because that would take too long. But I want to give you a sense of why this is really true. So let's say I is the integral from minus infinity to infinity of e to the negative x squared over 2 dx. Okay? I want to show that this equals the square root of 2 pi. Because then if I divide by the square root of 2 pi, I get 1. So if I square the integral, I'm going to write it, and I'm going to use a different variable for the second one. I'll use y. So this is the same as a double integral. So part of this is to show you where calculus goes. So I have e to the negative x squared plus y squared over 2 dx dy. And so I'm integrating over the entire plane. And now I'm going to change variables from xy space to r theta space. And so here we have x is r cosine theta, y is r sine theta, and the hard one is the area measure dx dy is r dr d theta. To give you a quick sketch as to why that might be true, here's the circle x squared plus y squared is less than or equal to 1. What does this look like in polar coordinates? R is less than or equal to 1. So here is my x and y axis. If I look at it in r theta space, this is now just the equation r is less than or equal to 1. And then 0 less than or equal to theta less than or equal to 2 pi. So here's 2 pi, here's 1. So a circle in polar coordinates is a rectangle. And so integration is really nice. When we have rectangles, we can basically just do calc 1 twice. That's why we do this change of variables. So if you look at what's going on in a circle, here's r plus delta r. And let's say this angle was theta. Here's theta plus delta theta. So this is my small little extra region. And if I want to figure out what is the area of this region, so I've increased r and I've increased theta by a little bit. Well, the arc length here and the arc length here is approximately the same. Or another way of looking at it is the area of the big circle is pi r plus delta r squared. Then I subtract off pi r squared. And that's going to give me the area of the whole annular ring. And then what fraction of the annular ring I have? I have delta theta over 2 pi. If delta theta was all of 2 pi, I'd have the whole ring. So I then multiply this by delta theta over 2 pi. So when I expand things out, the pi r squared cancels the pi r squared. Then I get a 2 pi r delta theta over 2 pi. So this is going to give me a r delta theta. And then the other term I'll have a pi delta theta over 2 pi. And if you look in the limit as delta r and delta theta go to 0, this is 2 infinitesimals. This is 3 infinitesimals. So this becomes negligible in the limit. This is where the r dr d theta comes from when we go from dx dy to r dr d theta. The better way of viewing this is you should really view this as dr times r d theta. Because it's r times the theta that's a length. And so again, I'm just trying to give you a rough sense of what's going on. So my integration, I now get I squared is the integral r goes from 0 to infinity, theta goes from 0 to 2 pi, x squared plus y squared becomes r squared. So I get e to the negative r squared over 2 r dr d theta. The theta integration, well, this has no theta dependence. So when I do the theta integration, I just get 2 pi. And then I have the integral r goes from 0 to infinity of e to the negative r squared over 2 r dr. Well, if you do your u substitution, I need exactly a negative r. I've got a positive r, so I just flip the order of integration, and so I'll get 2 pi e to the negative r squared over 2 at 0 and infinity. At 0 I get 1, at infinity I get 0, so I just get 2 pi. So I get the square is equal to 2 pi, so this has to equal to the square root of pi. So this is the rough sketch of why it integrates to 1.
That's a neat trick.
It's an incredible trick. This is another example of you take a step backwards, take steps forward. It's absurd that the way you evaluate this integral is you convert it to a two-dimensional integral. You need to know the correct change of variables. And this is one of the hardest things in multivariable calculus, is how do the things change. So, this is the last hour of the last day. This is where you put in the really heavy-duty stuff. All right. This gives you a sense of where things go. So let me go back to Stirling's formula and to try to estimate factorials. So the question is, who cares about estimating factorials? Why do we care about what n factorial is? So if n is large, n factorial, it's n times n minus 1 times 3 times 2 times 1. It's approximately n to the n e to the minus n square root of 2 pi n. And then it's equal to times 1 plus an error of size 1 over n plus an error of size 1 over n squared plus dot dot dot. So almost like a Taylor series expansion. The main term stops here. The next term is like 1 over 12n, much smaller. OK, so why would we care about estimating factorials? We use factorials all the time. N choose k. This is the number of ways to choose k objects from n when order doesn't matter. This is n factorial over k factorial n minus k factorial. So just so I know what levels to pitch this, how many people are comfortable that n choose k is this, and it's the number of ways to choose k objects from n? How many people are not comfortable with this? Everybody's comfortable that n choose k is this. OK, good. So this is one reason why we might want to estimate factorials. So there's a lot of ways to try to estimate what n factorial is. And probably the best is to use the integral test from calculus. So we have n factorial. So if you want, f of n is n factorial. I want to calculate this function. I have a product. I don't like products. I like sums. So I tell my students, you should have a Pavlovian reaction anytime you see a product. What should you do whenever you see a product? So how do you convert a product to a sum? What should you do to it? I want to convert a product to a sum. Do we have anything that converts products to sums? Any transformation? And we've seen the transformation today. This is a highly integrated lecture. There's an advantage to walking an hour in the morning. What have we seen before that converts products to sums? So we have a function where if you apply this function to a product, you get a lot of sums. When we were doing regression was a I'm sorry?
The least squares.
Right. What function did we use to convert something that was not linear to something that was linear? Logs. The log of a product is the sum of the logs. So let's let g of n be the log of f of n. If I can estimate the log of my function, I can exponentiate. So this will now be the log of 1 plus the log of 2 plus the log of n. This looks a lot like the integral from 1 to n of the log of t dt. And so now the question is, what function has derivative log t? And I get to use one of my favorite methods of mathematics. I know I mentioned this in one of the earlier lectures. It's the method of divine inspiration. So if you write down the answer and it works, it's right. So t log t minus t, if you take the derivative of that, you get log t. Right, so if you integrate, so if you just guess, well, let me start off with t log t and take the derivative of that. The derivative of t is 1, so you get 1 times log t plus t times the derivative of log t is 1 over t. So I would get log t plus 1. So it's almost the derivative I want. It's too large by a 1. So I want to subtract 1. So what function has derivative negative 1? Negative t. And there you go. So if I wanted to actually find a function whose derivative was log squared or t log t, can you find that? Nice homework problem. So once you have one divine inspiration, you can often generate subsequent divine inspirations. So I'm being very fast and loose right here, but if I just approximate this sum with this integral, I'll now get t log t minus t, evaluated at t equals 1 and n. So this would be n log n minus n. And now when I put t equals 1, the log of 1 is 0, and then I'd get an extra minus 1. But actually, it becomes a minus, becomes a plus. So I would get the log of n factorial is approximately equal to this. So n factorial is about e to the n log n minus n plus 1. Well, e to the n log n is n to the n, e to the minus n, and then we just have an e. I'm not horribly off. And the reason I'm making a little bit of a mistake is, well, I'm truncating this exactly at n. I'm starting this at 1. I need to do a little bit of more care with the endpoints. And if you want to get a sense of how much of an error you're making, well, the last, maybe I should be integrating up to n plus 1. And if I integrate up to n plus 1, I would have an extra log n. If I exponentiate log n, what do I get? So if you exponentiate log n, so if we had an extra plus log n, when we exponentiate, what is e to the log n? N. That would give me an extra factor of n here. The actual value is square root of n. That's actually the geometric mean of 1 and n. 1 times n square root, it's on the order of square root of n. So we were talking about the arithmetic mean, geometric mean earlier today. This is actually a situation where it happens in practice. My error is essentially the average of the last term and the term I'm missing over here. So I would have a 1/2 log n plus 1. And a 1/2 log n plus 1 is the log of n to the 1/2. That's the log of the square root of n. That's the square root of n. It's a bit more work to get the square root of 2 pi. But the point of this is to just give you an idea that this is reasonable. So are people happy that this is reasonable for n factorial? So before we do the central limit theorem, I want to show you another way to attack this by using the Pharma-Brown problem. There should be an application of these cows that love these rectangular pens. So how many of you have seen the integral test in calculus? So for the integral test in calculus, which is what we're really using here, I'm assuming I have a situation where I have a function that's monotonic. It's either going up or going down. And so here, my function is going like this. And so if I approximate it from below, the area under this curve is going to give me an upper bound for the sum. Or if I do my sums the other way, like this, it's the same sum, but now the integral up to here will be a lower bound. And so I can get an upper and a lower bound for the true sum and use the integral test to convert calculating the sum to calculating an area. OK, I want to do the Pharma-Brown version of Stirling's formula. And the reason is I always like to see how good of a job can you do elementarily. In the interest of time, I'm not going to worry about if I have n halves, well, what if n is an odd number? I'll assume my n is a nice power of 2 just to make things clean. So I want to estimate 1 times 2 times 3 times n. Let's do this the way we did the zombie problem. I want an upper bound and a lower bound. It can be the stupidest upper bound. It can be the stupidest lower bound. What would you give me as an upper bound? Stupid upper bound. Why 2 as an upper bound? That's almost the lower bound. Your bound is a little bit high for a really stupid lower bound. What's a really stupid lower bound?
Lower.
Lower. All right, but 0 is too stupid. 1. But I'm going to write 1 in a better way. It's less equal to 1 to the n. So how do I get 1 to the n as a lower bound? So how could I get 1 to the n as a lower bound for that product? I'm sorry? Well, but I want to do this for general n. 1 is equal to 1. Is 1 less than 2? Is 1 less than 3? So if I replace every term in the product with 1, I can't make the product larger. So that's where I get 1 to the n. So what do you think a really stupid upper bound would be? I'm sorry? N to the n. So the product is at most n to the n, and it's at least 1 to the n. All right, we know it's n to the n e to the minus n. N to the n is growing a lot faster than e to the minus n. So there's a huge difference between these two extremes. So the question is, which extreme is right? So what we can do is we can do what's called a diatic decomposition. And I think I did this before. Did we do, I can guess your birthday in 10 questions or less? All right. Somebody think of a day during the year. Or does somebody have a day? Okay? I'm going to guess your day in 10 questions or less, but if I'm wrong, you have to say earlier or later. Are you thinking of June 30th? Okay. Is it earlier or later? So with my first guess of June 30, I've essentially split the year in half. And now I know her day is somewhere in the second half. So June, so all of July, all of August, all of September. I'll go with, is it October 1st? So now I know it's somewhere between October 1st and the end of the year. So November, so I've got all of October, so I'll go November 15. So now I know it's somewhere in this range. Every time I guess, I have the error. And because 2 to the 10 is 1,024, and there's only 366 days in the year, or 365, I'll be able to get your day in easily 10 questions. I don't actually need 10. This allows me to be a little bit careless in where I put the dividing lines. Every time I guess, I have my error. We saw this when we did divide and conquer. Every time we guess, we have our uncertainty. So what I'm going to do is I want to do a dyadic decomposition to try to approximate this better. So what I'm going to do, did I erase it too fast? Or?
No.
Okay. So 1, 2, all the way up to n halves, and then n halves plus 1 all the way up to n. In this range, it's between 1 to the n halves and n halves to the n halves. And here, it's between n halves plus 1 to the n halves and n to the n halves. I'm only going to work on the upper bound. You could do the lower bound. You don't want to see me do twice as much algebra. So the upper bound, 1 times 2 times n, is going to be at most n halves to the n halves times n to the n halves. I use the upper bound for each one. That's much better than our n to the n. What do we get now? N to the n halves, n to the n halves, that's n to the n. And now we have 2 to the negative n halves. I can write this as n to the n. This is the same as the square root of 2 to the negative n, or approximately n to the n 1.414 to the negative n. I should have e, which is about 2.718. So the more times I do this, the better I'll get. So I could now break this up into each of these into half. And what you'll see is very quickly you come to something that's close. Right? I don't want to keep doing this. I want to just show you how you can use the Farmer-Brown problem, and make some good of all the walking I did this morning. All right, so then this way, some people will feel less guilty that I was walking. Unlikely. Trying to massage people's conscience. All right, so we have 1, 2, ... and halves plus 1. So let's pair everything up. So I'll do n halves minus 1 n halves. So I'll pair 1 with n halves. I'll pair 2 with n halves minus 1. I'll pair. So notice in all of these pairs, the sum is the same. Does this remind you of the Farmer-Brown problem where I have a fixed perimeter and I want to maximize the product? What's the maximum product? I'm sorry? So if I have two numbers that sum to, and so x plus y equals n halves plus 1, where is the product maximized? I'm sorry? So I'm then multiplying x times y. Where is this largest? Which pair? When they're equal? The middle. So 1 times n halves, and then 2 times n halves minus 1, and then 3 times n halves minus 2, all of these are going to be less than equal to the middle pair. The middle pair, will you allow me to just write as n fourth times n fourths? Really, they can't both be n fourths, but will you accept this? So I'm not going to worry about that small little bit of bookkeeping, but so each one of these products is going to be at most n fourths times n fourths. Okay? So what that means is this part over here is going to be less than equal to n squared over 16. And how many pairs do I have? N over 4 pairs. And over here, it'll be 3n over 16, 3n squared over 16. Because I'll have 3n over 4, 3n over 4 is the middle point. And how many pairs do I have? I have n fourth. So when I put this all together, I get 1 times 2 times n is less than equal to n squared over 16 to the n fourths times 3n squared over 16 to the n over 4. So I have n to the n halves, n to the n halves. I have n to the n again. So I have n factorial is less than equal to n to the n. Now it becomes a little bit worse. I have 3 over 16 squared to the n fourths. So I'll write it like this. So I need to take the fourth root of 3/16. What's the fourth root of 16? Oh, sorry, 16 squared, thank you. So what's the fourth root of 16 squared? 4. And so this is going to be n factorial less than equal to n to the n. I will flip it, so now I'll have 4 over the fourth root of 3 to the negative n. So does somebody have a calculator? So E is about 2.71828. Over here, we got 1.414 to the negative n. The correct answer should be about 2.71828. If I use the Farmer-Brown improvement, we now have 4 over the fourth root of 3. So what is 4 divided by the 4th root of 3? 4 divided by the 4th root of 3 is what? That seems. What's the 4th root of 3?
4th root of 3 is 1.316.
Okay. Okay.
Actually, 16 squared.
Wait, why the 3?
Yeah, it's 4.
Why 3n squared over 16?
I'm sorry?
Why the 3? You're going to the middle of this.
Right, the middle of the second one, which would be 3n over 4 times. Oh, this should be a 9.
Yeah.
This should be a 9. Thank you. So that should be a 9. There we go. Because it looked a little bit off from what I remembered. So that should be a 9. So I'll do it as 3 squared. There we go. 3 squared over 16 squared. So it's going to be 4 over the square root of 3. All right, that's better. So the square root of 3 is about 1.7. So it's 2.309? That's better. 2.309. 4. So if you look at this, we had 1.414. By just doing the Farmer-Brown tweak, we're now at 2.3, and the correct value is 2.7. So we could keep doing this divide and conquer. We could split this in half and this in half. And if we use the Farmer-Brown modification, it'll converge a lot faster than this. So I wanted to show you this problem because it's sometimes nice to see how far you can push elementary methods. And once we do this problem from calculus that we know that things are maximized in the middle, well, here's a really nice application. And so if we want to approximate n factorial for very large n, this is approximately it. So if people want, for the last few minutes, I can now give you a quick sketch of if you toss a fair coin, a huge number of times, it should be approximately a Gaussian. So if you want, I can definitely give you, handouts with the algebra. The calculation here is very standard. The challenge is finding a way to do it so that the algebra is not too overwhelming. So we will toss a fair coin 2n times. It's more convenient to toss it an even number of times. And a head will be a +1, and a tail will be a -1. So every time you take a head, you take a step to the right. Every time you get a tail, you take a step to the left. They sometimes call this a random walk, or they sometimes in textbooks talk about a drunk staggering home from a lamppost late at night. And so I remember the physics textbook we used said the primary purpose of physics is not to help drunks staggering home from a lamppost late at night. And I like how they said the primary purpose, so that a secondary purpose of physics is to be concerned with drunks. I've always thought it would be fascinating to have a modification where you have a infinite line, and the question is, will the drunk get home? And you put a bunch of bars at various points, as well as a bunch of Starbucks, so that the drunk could actually get into a bar and get another drink and become even more drunk, or they could actually enter a Starbucks or a Dunkin' Donuts, have a cup of coffee, and start to sober up. And so there's a lot of interesting dynamics you could do. So let's try to calculate what is the probability we are 2k from the origin. Notice we can only be an even number from the origin, right? Because we have an even number of tosses. Every head is +1, every tail is -1. So to be that, we would need to have n plus k heads and n minus k tails. And that would give us a distance of 2k from the origin. So what's the probability? Well, I have 2n tosses, and I have to choose n plus k of them to be a head. And then I have n minus k tosses left over, and they all have to be tails. Well, what's n minus k choose n minus k? It's 1. I just have to choose them all to be tails. So it's just 2n choose n plus k. And then the probability of each sequence is 1 over 2 to the 2n. Because each head has probability 1/2, each tail has probability 1/2. So the probability of a specific string of heads and tails is 1/2 to the 2n. And the number of those strings that have n plus k heads and n minus k tails is 2n choose n plus k. So I just need to calculate what this probability is when n and k is very, very large. I'm going to skip a little bit of the algebra in the interest of time to just give you a sense of the main idea. The claim is that k has to be very, very close to 0. That you would expect you have roughly the same number of heads and tails. The question is close on what scale? And the scale is on the order of the standard deviation. It's on the order of square root of n. So you don't expect k to be much larger than, say, square root of n or a bit more. So let's just try to analyze this. So let's analyze 2n choose n plus k. So this would be 2n factorial over n plus k factorial n minus k factorial. How should we analyze this product? What should we do? So I've got a ratio of factorials. What could I use to try to understand the factorials? So I have Stirling's formula. And I can take logarithms. The log of a product is the sum of the logs, or if it's a quotient, the difference of the logs. So if I start using Stirling's formula, I'll get 2 to the 2n, 2n to the 2n, e to the negative 2n, square root of 2 pi times 2n. And then down below, I get n plus k to the n plus k, e to the minus n plus k, square root of 2 pi n plus k. And then I'll have n minus k to the n minus k, e to the negative n minus k, square root of 2 pi n minus k. So a lot of things cancel. Those all cancel. I have this 1/2 to the 2n. Let's keep that. So let's put back the 1/2 to the 2n. And if I keep that, the 2 to the 2n now cancels. So I still have the n to the n, but that cancels. And so what I'm left with, and I have a square root of 2 pi that cancels with this square root of 2 pi. And so we're left with n to the 2n, square root of 2n. Down below, I have n plus k to the n plus k. And then I have n minus k to the n minus k. And now I have a square root of 2 pi n minus k times n plus k. So n squared minus k squared. So is everybody OK up to this point? So now here's the thing. I'm going to assume that, say, k is less than or equal to n to the 3/5. That you're not going to be too far away. There are some elementary bounds in probability you can do. In the interest of time, it's getting late. I don't think you want to see all the details. Just k can't be that large. It's very unlikely to be too far away from the mean. You can go through and you can show that as k gets very, very large, this becomes very low probability. N squared minus k squared is approximately n squared. So this is really square root of n divided by square root of n squared. So this is going to give us like a 1/2 pi n down below. And the square root of 2 pi, that's coming in like the normalization constant that we had in the central limit theorem. So let's look at what we have. We have n to the 2n. I'm going to pull out an n from here and an n from here. So when I pull that out, I'll have an n to the n plus k and an n to the n minus k. Oh, that's going to perfectly cancel this. Right? So everybody agree that if I pull out an n from here and I pull out an n from here, I get n to the n plus k, n to the n minus k. That's n to the 2n, which cancels the top. So I'm left with 1 over 1 plus k over n to the n minus k, and then 1 minus k over n to the n minus k. And then this over here is going to look like 1 over the square root of 2 pi n. Is everybody okay roughly to here? So I can write n plus k as n times 1 plus k over n. So n plus k to the n plus k will just be n to the n plus k, 1 plus k over n to the n plus k. And by doing that, I can cancel the n to the 2n. Okay? So now I just need to figure out what does this look like as n gets very, very large. Is everybody okay up to here?
Sorry, I'm being slow, I guess. I get
No.
that part, but
What cancels out the square root of 2n anyway?
I have an n squared down below. And I'm saying because k squared is much lower than n squared, this is looking roughly like an n squared over here. And so,
why did the 2 stay?
I'm sorry?
Why did the 2 stay?
Oh,
You have square root of 2 and the square root of 2.
the 2 poly cancels. The 2 cancels. Okay, yes, the 2 cancels. So this part is no problem. I now just have to understand this piece. So I want to understand 1 plus k over n to the n plus k, 1 minus k over n to the n minus k.
So should that second one also be a plus? Sorry, the first one be a plus?
This one?
And the
Oh, this, yes, there should be a plus up here, yes. Yes.
okay, now,
And that's what I have over here. So how would I understand this quantity? I take logarithms. Because the log of a product is the sum of the logs. So now when I take the logarithm, I'll get n plus k, the log of 1 plus k over n, plus n minus k, the log of 1 minus k over n. And I'm going to use the log of 1 plus x is approximately x. It's minus x squared over 2 plus x cubed over 3, and so on and so on. Well, if k is small relative to n, the more terms I have, the smaller it's going to be. So let's look at what happens when I start to expand. So the log of 1 plus k over n, the first term is k over n. The next term is going to be minus k squared over 2n squared. The next term will be plus k cubed over 3n cubed, and so on and so on. And this is where I wanted to say k is no more than n to the 0.6. Because if I have k is less equal to n to the 0.6, then k cubed is less than n to the 1.8. So k cubed over n cubed is less than equal to 1 over n to the 1.2. So that even if I multiply it by a large number like n, I would still have a power of n down below and would go to 0. So if I can just say I don't have to worry about k that's larger than n to the 0.6, I don't have to worry about the third and higher terms. That's the part that I'm just going to have to just say, trust me, we're running out of time. You don't want to see the algebra to just show that it's OK. The probability of k being larger than n to the 0.6 is so small, we don't need to worry about it. There's some elementary results in probability that allow you to do that. If we can do that, I don't need to worry about this cubic term. I can then say, it's approximately this. And that those terms won't matter. Now, I do have to worry about this term because k could be as large as the square root of n. So then k squared is of size n times n over n squared is of size 1. Now this piece will be plus n minus k, and now I'll get minus this. So now I'll get a minus k over n minus k squared over 2n squared. All right? So let's look and see what happens. We have a k over n times n. We have a negative k over n times n. Those cancel. We have a k squared over n. We have a k squared over n. They reinforce. So we get a 2k squared over n when we just look at the main terms. This is not a good time, Sally, to walk in.
I'll do my best.
OK. Now let's look at the next piece. We have both a minus k squared over 2n squared in both of them. So when the n hits, they reinforce. And we will get a minus 2k squared over 2n. And then when the k and the negative k hit, they're opposite, so they cancel. And so this will give us a 2k squared over n minus k squared over n. So we get a k squared over n. So well, we have 2k squared over n minus 1k squared over n is just k squared over n.
Oh, yeah, yeah.
So now this was the logarithm. So if we exponentiate, we get e to the k squared over n. But because it was down in the denominator, this should be an e to the negative k squared over n. So you get e to the negative k squared over n, and you have 1 over the square root of pi n. So this is almost a normal with mean 0 and variance or standard deviation n. So I'm not going to do the rest of the algebra. This is enough to show you that it's coming close, and it's just a little bit of algebra at the end. One of the things you have to be careful about is I can only take on even values. So when I then compare it to the normal, my possible values are 0, plus or minus 2, plus or minus 4, plus or minus 6. So there's an extra factor of 2 you have to play with. What I wanted you to just see is you can begin to see it's looking like a Gaussian. The Gaussian was e to the negative x squared over standard over variance, and that's what we're getting. So the last thing, and then this is the day, is this was a promise I had made earlier about what the square root of what the factorial of negative a half is. So we've been doing a lot with n factorial. So it turns out there's this beautiful function called the gamma function, which is the integral from 0 to infinity of e to the negative x times x to the s plus 1 dx. And it turns out gamma of 1 is 1. And it's s minus 1. Gamma of 2 is 1. Gamma of 3 is 2. Gamma of 4 is 6. Gamma of 5, any guesses? 24. Gamma of 6, 120, or also known as 5 factorial. Gamma of n plus 1 is actually just n factorial. And the way you prove this is integration by parts. So if you have gamma of n plus 1, this is the integral from 0 to infinity of e to the negative x, x to the n plus 1 minus 1 dx. Okay, so this is just, let's let u, so dv will be e to the negative x dx. So v is just negative e to the negative x. U will be x to the n. du will be n x to the n minus 1. So now gamma of n plus 1, well, by integration by parts, I have uv. So I have negative x to the n e to the minus x at 0 and infinity, minus v du. The minus and the minus becomes a plus. The integral from 0 to infinity of n e to the negative x, x to the n minus 1 dx. Well, this is just n times gamma of n. When I plug in 0, I get 0. And when I plug in infinity, the exponential decays faster than the function. And we just get gamma of n plus 1 is n times gamma of n. And that's how you can then just prove this formula by induction. So, gamma of 3 is 2. So we now get gamma of 4 is gamma of 3 plus 1 is 3 times gamma of 2. Is 3 times gamma of 3, which is 3 times 2 factorial. And so gamma of n is just n factorial. Gamma of n plus 1 is just n factorial. Okay, so why do we care about this?
Where did that come from?
This gamma function?
Yeah.
So it is a continuous generalization of the factorial. So it is a way to talk about factorials at more than just the integers. And in fact, another way to prove Stirling's formula. So we proved while you were gone that n factorial is about n to the n e to the minus n squared of 2 pi n. This is Stirling's formula. So one way to prove that is to actually say gamma of n factorial is gamma of n plus 1 is this integral, and then approximate this integral. So this is, part of it is trying to show you where does calculus go, where does analysis go, where does math go. By taking a discrete function and finding a continuous function which takes on these values as special cases, I can now use the techniques of calculus to estimate something that's discrete. And so if you want, this is the real bullshit stage of the lecture. So we have n factorial is gamma of n plus 1, and this is equal to the integral from 0 to infinity of e to the negative x, x to the n dx. So this is my integrand. F of x is e to the negative x, x to the n. Where is the integrand largest? How would you find where the integrand is largest? I'm sorry? Take the derivative. So f prime of x, so I use the product rule. It's negative e to the negative x, x to the n, plus e to the negative x, n, x to the n minus 1. So I get e to the negative x. I pull out an x to the n minus 1, and I'm left with negative x plus n. So where's the critical point? X equals n. What's the value of the integrand? F of n is n to the n e to the minus n. So what I'm basically saying is the largest value of the integrand is n to the n e to the minus n. And Stirling's formula is n to the n e to the minus n squared of 2 pi n. There's some way to approximate this around its largest value and talk about how quickly it decays. So there are powerful techniques when you can use calculus. We saw this when we were doing the method of least squares in linear regression. We use squares and not absolute values because with squares, calculus is available. And when you're talking to your students, why do we try to make these things rigorous? Why do we develop all these careful techniques? I can now use this to understand n factorial. And so this generalization is very useful. So I will end with 2 examples of why we care about this generalization. One of them allows us to bypass the polar integration. So I should be able to do the change of variables on the fly. Let's look at gamma of 1/2. That's the integral from 0 to infinity of e to the negative x, x to the 1/2 minus 1 dx. Let's let x equal u squared. So then dx will be 2u du. So gamma of 1/2 is going to be the integral from 0 to infinity e to the negative u squared. Now this is an x to the 1/2. negative 1/2. X to the negative 1/2 is the same as 1 over u. So I'll have a u to the negative 1 times 2u du. This is twice the integral from 0 to infinity e to the negative u squared du. This is the integral from negative infinity to infinity of e to the negative u squared du. This is almost the same as what we had before. The only difference was we had e to the negative x squared over 2. So you just do one more change of variables. So essentially, the way we get the normalization constant for the Gaussian is calculating gamma of 1/2. It turns out that this integral is the square root of pi. There's a lot of ways to prove this. I showed you one with a polar trick. There's other things you can do. So this would be the strange formula to end everything on. I'll go to bright red. So gamma of n plus 1 is n factorial. Gamma of s plus 1, more generally, is just s times gamma of s. So what we're going to do is we're going to extend the factorial function. And we're going to say that in general, gamma of s is going to be s minus 1 factorial. This agrees with our notion of the factorial when it's a normal integer. But it gives us something new and strange. So if I put in 1/2, I get negative 1/2 factorial is equal to the square root of pi. So the number of ways of arranging negative half of a person is equal to the square root of pi. So you can do the change of variables here if you let v equal the square root of 2 times u, so u equals v over the square root of 2, then this integral over here would become the integral from minus infinity to infinity e to the negative v squared over 2, and then du is just going to become dv over the square root of 2. And we knew that this integral was just the square root of 2 pi, so that means this integral, just the top, must be square root of pi. And so, but based on the polar trick we've had, we've now computed that gamma of 1/2 is the square root of pi. So we lose the geometric interpretation, the physical interpretation of the factorial. I do not know what it means to take the number of arrangements when order matters of negative half of a person. But if I could, that's what it would be. We talked about how if you use the geometric series formula, 1 plus x squared, this is equal to 1 over 1 minus x if the absolute value of x is less than 1. If the absolute value of x is greater than 1, this makes no sense. If I talk about 1 plus 2 plus 4 plus 8, this equals negative 1? The formula on the right makes sense as long as x doesn't equal 1. It's just we lose the interpretation we had from before. So similarly, this formula makes sense. I can put in 1/2, and the integral makes sense. The integral is well defined. I get the square root of pi. I just lose the physical significance that it's just equal to some kind of ordering for arrangements. So I realize this, might have been better to end the day with zombies and start the day when people are tired with the advanced mathematics. But the very last bit of any series should be, so where does all this shit really go, down the road? And this is the best connection I could think of all the different stuff we've been doing. It pieces them all together. The Pharma-Brown problem comes in terms of trying to come up with elementary estimates. The idea of whenever you have a product, you want to take a log. If you can get your students to understand that a logarithm is designed to transform data so that it might be more visually understandable, that would be a phenomenal skill for them to get in going to college. And then when we wanted to do the analysis, taking the logarithms really helped us for doing the analysis. Then there's a lot of algebra that just has to be done. And if you do it on the board, you'll make mistakes. But if you go through it very carefully, eventually things will balance out. And what's wonderful is we get this behavior, this central limit theorem, this Gaussian decay of just tossing a fair coin. You can do it if the coin is not fair. The analysis makes this look really nice. in that case. But anyways, it's been a lot of fun coming and talking, and hope to be able to come back at some other time. So thank you. It is also